questions for me?
I know them. Actually, I know she can do some attorney's sisters. Okay. Okay. I don't really know people.
Well, we kind of give a couple of pointers, or maybe three, I don't remember how many, on the scattering parameters. There's more on the topic, obviously, but you may consider that as an introduction to the topic. If you'd like to read more about it, there's plenty of resources that you can get more on the scattering parameters. Well, the book has a decent coverage as well. So I'll leave it at that, and then we'll move on to waveguides. I sent you yesterday some slides or some copies of pages of other resources on planar lines, which we plan to cover at some point. But that could be a good resource for preparation for the lab, because I believe some of you in the laboratory will get involved in planar lines before we formally cover it. Well, we delayed talking about waveguides, so we'll get started with that. And two main configurations, two main geometries that we typically talk about in waveguides, which are the rectangular waveguides and cylindrical waveguides. And the concept of the waveguide is an arrangement that we do to guide the wave. So when you really think about the transmission lines and waveguides, because otherwise you can send your waves up in the air and they would go and they would reach destinations. But obviously with your antenna you can kind of do some directional propagation, or you can do omnidirectional propagation. Waveguides are designed to take the signal from a specific destination to another, a specific source to a specific destination. It's a way to confine the flow of the signal. Just like when you think about water flowing in a hose kind of thing, right? You confine the flow into a specific concept. Now, you can talk about metallic waveguides, conductor, or dielectric waveguides. Dielectric waveguides typically are used in the millimeter range as well as optical range. Metallic waveguides are typically used in lower frequencies, lower than those, right? I'm not talking about DC, obviously. I'm not sending megahertz. We're talking here about still gigahertz, but not quite reaching into that. The metallic waveguides, basically you have a conductor, it's shaped a certain way, like a rectangular, or a circular, or any other shape you can think of. Obviously, if we're going to analyze that and develop some design criteria so we can design them, we need something that we can write equations for. So typically these are the two shapes that are easy to write equations for relative to other forms, if you have a rectangular or any other shape. And as it turns out, that the rectangulars actually give you the best performance, although it's a harder thing to manufacture compared to a circular. A circular is a pipe, you can draw a pipe, you've seen pipes everywhere, right? But you haven't seen a rectangular pipe. right? Although in air ducts, they make them rectangular, right? But not always, some of them are also circular. In the dielectric guides, you can have the same kind of shapes as well, because it's a matter of manufacturing. In addition to these two shapes, you can also have the parallel situation, which is typical of planar manufacturing. When you do things in substrate format, you are doing planar configuration. The vertical and the round. This is difficult, obviously, in planar. You can't build a circular thing on a substrate, right? You can probably do that by building some vertical shorts, but typically that's also another configuration that is typical. So the parallel or the planar configuration, the rectangular, the cylinder. Now, in the metallic, you will have metals here, or conductors. You'll have conductors here. You have conductors there. That's the metallic. Right? In dielectric, it will be, well, obviously, once you have a metal here, then you are, whatever you have here doesn't matter. Right? Because supposedly the conductors provide shielding and confinement that your signal will not leak out, right? Assuming obviously the conductor is thick enough, it doesn't matter beyond that, because you have a certain thickness for the skin depth that the signal will penetrate through, but if this is thick enough and you go beyond multiples of skin depth, you are in good shape. For dielectric, typically you will have dielectric 1 and dielectric 2, or maybe even more. Right? Because, if you leave that open, obviously that's free space. Even if you don't put anything there, that's free space already. So typically you have two dielectrics. You can never have one dielectric alone. So this is your dielectric that you make your guide from, and this could be a free space, or it could be something else, and this could be a free space, right? Same thing with a rectangular shape, right? We'll have, again, epsilon 1, epsilon 2, epsilon 3. It doesn't have to be that way, because epsilon 3, if that's free space, that's everywhere, right? In a planar configuration, again, you have an epsilon here, 1, you have epsilon 2 down here, you may have an epsilon 3, you may have an epsilon 4, you may have a dielectric underneath, dielectric above, and free space, and this is your main media where you're propagating things. Dielectric waveguides are common in the optical region, known as fiber optics, right? And they are made of glass, special alloys of glass, or special, I shouldn't say the word alloys, special glass, what would be the proper term for that? Okay. And possibly also all forms of other dielectric media. Could be plastics, could be, in case of planar, could be layers of silicon, whatever it takes, to build that. And obviously the characteristics have to be suitable to the frequency range of that. In all these cases, you can develop an RLCG model for those. Right? That would be too primitive and too naive. Right? Okay? And it's too hard as well. Right? So what we do is we do the right thing, which is start with field analysis. We start with Maxwell's equations, we write the equations, and we solve those differential equations, apply the boundary conditions, and we get the solutions. And that's actually what we should be doing also with transmission lines. But if I do the circular one, it will be a step towards that, because all what I need to do is add the center conductor and my boundary conditions, and I get the transmission line solution. And I can see in that case, the higher order modes that I ignored in my circuit theory analysis. When we did the circuit theory analysis, it was an oversimplification and an approximation to the lower order number. So we start with Maxwell's equations. So we remember Maxwell's equations? Now we know Maxwell's equations. We can write them in so many configurations. We can write the frequency domain, the phasor domain, we can write the time domain, we can write the point form, we can write the integral form, right? The most convenient one to work with is typically the point form in the phasor domain, right? Point form in the phasor domain. And the reason for that is the point form gives you a differential equation, right? Well, the integral form, you have to talk about the whole thing as a holistic thing. You know, things here are influenced by there, and you just, the equation, it's not suitable except for symmetrical situations. The integral form, typically the analysis of integral forms are good only for symmetrical situations. And we use them when, you know, we had a uniform sphere or a uniform cylinder or a uniform plane, you know, nothing changes ever in other coordinates. You know, so we write them in the point form. And we also said we phase the domain or harmonic analysis, right? I just want to go to the side for a second here to explain the point form versus the integral form. Because sometimes we have a misconception about that. Suppose I want to give you a function. The point form tells you that partial f partial x is equal to, I give you that, and I give you some initial conditions or boundary conditions that x1 is equal to this, f1, f of x1 is equal to that. I give you that, right? So when you solve this differential equation, you can get the function. Okay? Well, the integral form does the following. It tells you integration from a to b of f of x dx is equal to that much. So it's giving you the area under the curve, for example. This is the point form and this is integral form. Now, this does not yield a unique solution unless you have some uniformity. Like you know that this was a straight line, right? I have to have that something about the nature of that equation to be able to solve that. Okay. If it's a straight line, then I can say yes, I can assume this in the form of alpha x plus beta and integrate and get that, and therefore I can get the alpha and beta. Right? Or if it was a constant, for example, or if it was a parabola, whatever it is, I have to know what the nature of that equation to be able to solve it. Because you cannot extract f of x, outside the integration, unless you know you have constant that you can extract. Well, this one here is more robust, right? It just tells you that you can get your information through the integration of that or solution of that differential equations. That's why the point form is preferred. Right? This is again the point form, integral form. Phasor versus time domain. Which one? I think we had a discussion of that sort earlier, and basically, time domain is the real thing, right? And it can handle linearities and non-linearities, and you know, it can do all these kind of things. But the math may get beyond our interest, right? I'm not going to use the word ability, okay? It may get beyond our interest. While if I do phasor domain, the math is much more straightforward. And basically, The only thing is that you are limited to linear systems. Linear media, non-linearities are allowed if you are working with frequency. Now, how do you get, if I'm assuming here that the excitation is sinusoidal, how do I get other forms of excitation? Then we use Fourier to help us with that. If I have any source that's not sinusoidal, let's say whatever the shape is, I can expand that source into a superposition of several sources, right? That's what the harmonic analysis of the signal produces, the Fourier analysis. You can get F1, F2, F3, you can get all the frequency ingredients of that signal by doing a Fourier analysis. So that signal is equivalent to those. So if that is being imposed on your system, your network, your device, or whatever, your system, right, then you can simply say this is the superposition of several problems. F1, F2, etc. By superposition, when you have multiple sources, you just kill all the sources but one, get the solution for that, and repeat, and add the solutions. So you sum all the solutions here, you get the solution to that. So by solving for one frequency, I'm actually solving for any other combination of frequencies, and I can get the gel solution. So solving for one sinusoid is not limiting, it's not a special thing, it's basically a component of the whole, and rather than work with the whole, I just work with one at a time.
Sorry, you said this is assuming we have a linear system?
Absolutely, absolutely. Without the linear system, sigma cannot be used, right? Superposition requires and necessitates that you have a linear system. Linear media, everything should be. Non-linearity is allowed. So when I'm doing that, I'm really working a very powerful solution because I can solve any other case, but not linear, obviously, using this scheme. Now, I'm not going to worry myself about which particular shape I have at this point. I'll leave that to a later phase, but what I will say is I have to assume that whatever shape it is going to be uniform in one coordinate, right? That's the concept of the waveguide or the transmission medium. Well, at some times you have bends and twists and stuff like that. I'm just going to leave those aside for now. So I'm analyzing a uniform thing, and I'm going to pick the z-axis to be that thing, right? That's the typical situation. So I'm going to assume uniform cross-section. Along z-axis. The cross-section is uniform everywhere. Should I say along or everywhere along the z-axis? Everywhere. Cross-section is the same. And I'm going to just do the general solution. Let's write Maxwell's equations. I haven't written them. I thought we already did. Okay. How many equations do we have?
4.
How about 7? 4 and 3, right? 4 are the main equations, and 3 are the constituent relationships, right? The one that relate the parameters to each other depending on the material of the medium. Okay. So we start with curl H, curl E, div D, and div B. These are the 4 main equations, and the 3 others are B versus H, D versus E, and J versus P as well, right? All these vectors, phasors, so I should write the arrows here, and whichever way you want to distinguish phasors, writing them as an uppercase is typically what we use for phasors, right? If we use in the time domain, we usually use lowercase quantities, but that way they are phasors. And I'm adding the vector signs. Now, I'm going to also assume that my media is homogeneous, so I don't have to worry about tensors, right? Typically, if you assume homogeneous media, it means whatever you do in the x-axis will be the same as you do in the y, you do in the z, same thing. So if I write here mu h, mu is constant everywhere, x, y, or z. Otherwise, you have to worry about a vector b and a vector h and a tensor of mu's, mu xx, mu xy, etc. Right? You can have that. That is an additional complication. This one here is epsilon, and this one here is sigma, right? Epsilon is the permittivity, mu is the permeability, sigma is the conductivity of the media. Now, I have a few easy things here to write. This one is a 0, right? You all remember that. And div d is what?
Is it 0 as well?
Hmm?
Is it 0 as well?
No.
Volume charge density?
It would be 0 in special cases, but in general it would be
Volume charge density? Volume charge density.
rho,
Rho sub V.
rho sub v,
Or epsilon E.
hmm?
Epsilon E.
I can't hear you.
Epsilon E.
Epsilon e, when did we have fields last? Long time ago. What's rho sub v?
Volume charge density.
Volumetric charge density. Any charge? Or do we add the subscript F? The free charges. Right? The free charges in the media, the volumetric density contribute to the divergence of E. Now, we used to call this something other than Maxwell's equations. Before we learn about Maxwell, what did we call it? Gauss's law. Gauss's law says, all right, if you have some charges, these charges will act as a source of something, right? And that something, we call it the flux. Just like this light here puts out flux. The heat source puts out heat, right? So every source puts out a flux of something. So the charges put out the electrical flux. And the electric flux is equal to that charge. Right? We chose the units to be the same. It's a choice. Okay. So we chose that. The density of that flux, that means how much flux per unit area that it intercepts. The density. Right? We got that flux, so I measure the density by crossing that with a unit area and see how much flux crosses that, and that's what we call D. So D is the flux density, how much flux that, and that relates to the volumetric charge density, and the proof of that is straightforward. It takes about half a page or so to prove that. But the concept is that the divergence of that flux density is equal to the volumetric charge density. So how come this is 0?
There are no free magnetic charges.
There are no free magnetic charges, simply because the way magnetism, see the nature of electric flux and magnetic flux are different. The charge puts out the electric flux out. The magnetic flux comes as a result of the motion of the charge. Charges, when they move, they will cause a circular current, right? There is a current, right? And that current is responsible for the magnetic flux. So if you look at the charge in motion, that's always a closed loop. The current that's produced by the charge is always a closed loop. And that closed loop will have a flux that link with that loop. So it will produce, if you want to think about charge polarity here, so you think about the magnetic phase on the top is positive, the magnetic phase on the bottom is negative, and they are always complementary to each other. You can never have one without the other. So you cannot separate magnetic charges into plus and minus. They're always coming in doubles. They're always coming in dipoles, right? So because we always have dipoles here, right? On any level that you can think of, and I'm sure you remember in earlier here that you probably learned about when you take a magnet and you break it, you always have a north and a south. No matter how small you break it, you always have the dipole in it. So you can never separate them. So you can never have a positive charge separate from a negative charge. They always come in pairs, so they cancel each other. Okay. So the magnetic flux has a zero divergence. Divergence is zero, because they're always loop. The magnetic flux always forms in a loop. You can never have a flux line like this. In the electric situation, you can. A charge plus and a charge minus, and that's your flux line in the electric situation. Here you always have B comes in loops, so there's no divergence. Divergence means something that emerges. But if it comes back on itself, there's no divergence. The loop, you can never break the loop. It's not breakable. All right? This is called Ampere's law. Now, let's write it here. Gauss. This is Gaussian magnetism, both of these. This is what we used to refer to as Ampere's law. And says curl H is equal to J plus partial D partial T, which in the harmonic domain we write as J omega D. Okay? That's Ampere's law. In the time domain is J plus partial D partial T. This is Faraday's law. And Faraday's law talks about the circulation of E. The circulation of E is related to the magnetic flux linkage. The rate of change minus J omega B. Minus partial B partial T, which is minus J omega B. Partial T converts to a J omega. These are Maxwell's equations in the frequency domain in the point form. Well, we did solve these in plane wave propagation, right? And we got the wave propagation. We've seen the wavelength and the phase velocity and all that. So we have to go through some of that before we can apply boundary conditions. So if we're going to do this, we're going to avoid complications. Like I said, we're going to just take the straight section of the guide. We're not going to go to the bends or the twists or connectors or what have you. We can also ignore the source and the load. So if you have a waveguide, let me draw that right side here, so that will be a continuation. So I'm going to assume now that I have a source, antenna or what have you, and here's my waveguide, and then there will be a load, a receiver or what have you, or a termination. I'm going to do my analysis for this part. I'm going to stay away from any difficulty to start with. And we're going to assume that we have uniform cross-section, we said. I'm going to further assume that I don't have anything else in here, like maybe a repeater or what have you, nothing. So it's going to be source-free. In addition to being uniform and homogeneous, and linear and all the things that we mentioned so far, we're going to assume it's source free. Passive, conductor or dielectric, no sources. And if I add that source free thing, right away, I kill a few elements in this equation. What do I kill? Rho sub v for sure, right? No charges. So source free will kill rho sub v, will kill also any currents. Right? No currents in the medium. J is 0. These are the sources that we know. Charges and their motion. Charges rho, motion J. Now, if I put this to that, that means div epsilon E is equal to 0. And div is a differential operator, right? The divergence is a differential operator. And when you operate on a product, right, you have to worry about the derivative of the first and derivative of the second. But if the first is constant, that means I can take it out. We said it's uniform homogeneous, all right? So that can come out. So it's epsilon, the divergence of E is equal to 0. That's homogeneous medium. That means div E is 0. Likewise, div H is 0, right? If I do the same thing on the div G. So I go back here now, and instead of rewriting these equations, I'm just going to use the same space. And if you're taking notes, you can rewrite them. This is going to be J omega epsilon E and this is J omega mu H, and we're right here div E is 0 and div H is 0. These are my new Maxwell's equations. I don't need those anymore. I already reduced everything to E and H. Now these are simultaneous equations, right? E is here and there, and H is here and there. Typically what we do to solve them is, substitute one and the other. So I need to do a curl E. To get that here, that means I have to do a curl E. That means I need to do a curl on this equation. So I can get curl E to put it here. So I go to vector identities, the curl of a curl. Curl of A is equal to the gradient of the divergence of A minus delta squared of A. That's a known vector identity. So I borrow that. I'm going to erase those because I need that space. So I have the gradient of divergence of H minus del squared of H is equal to J omega epsilon curl of E. Right? Put that in there, and the divergence of H is 0. I end up with minus del squared H is equal to J omega epsilon curl of E, we get this, minus J omega mu H. minus j squared is plus, have another minus here, end up with del squared h is equal to minus omega squared mu epsilon h. And if I do the opposite, so I can write similarly, del squared E is equal to minus omega squared mu epsilon E. If I did the opposite, like did the curl here and substituted there. So one or the other. You can use one or the other. What we've done here now is combine two first order differential equations into one second order differential equation. But they are separable now. Here they were simultaneous. This one is separable. That means I can work either of them alone by itself. I've been writing a chapter on this for the past month, and I haven't finished more than about maybe 15 pages or so, and I haven't gotten to a point where it is near complete. I think that chapter is going to be close to maybe 60 or 70 pages. And what's slowing me down, obviously, studying all these equations, really were very time-consuming. I'm going to send you what I have. But, I don't think I applied the boundary conditions yet. So I'm still